Hi guys, in this video we'll take a look at reversing differentiation, rules for integration, integrating ax to the n, examples, and then we'll finish with a summary.
So how exactly can we reverse differentiation? When learning about some process, we often want to be able to know how to undo it. So suppose we want to expand some brackets, say the brackets x plus 2 and 2x minus 1. If we expand this out, then we get 2x squared plus 3x minus 2. We also want to be able to factorise this expression back into the brackets on the left-hand side. Similarly, let's say we have a recurring decimal, 0.9009, where the recursion occurs between the nines. We'd like to be able to write this as a fraction, and it turns out that the appropriate fraction is 91 divided by 101. But given 91 over 101, we'd also like to be able to write it as a recurring decimal, to undo the process. When we're given an equation of a curve, we are able to find its gradient by the process of differentiation. If we have that y is equal to x squared, then we can apply the process of differentiation and we get that dy by dx is equal to the derivative of x squared, which is equal to 2x. Again, this process here is called differentiation. Reversing differentiation allows us to help identify the equation of a curve corresponding to a given equation of its gradient. Suppose that we're given the gradient of a curve, and we have that dy by dx, the gradient, is equal to 2x. Now the equation dy by dx is equal to 2x produces as its possible outputs for y is equal to x squared, and then we have this plus c. For any value of c, where c is a constant, if we differentiate this expression x squared plus c, we will get 2x. Remember that a constant differentiates to 0. This is the process of reversing differentiation, and we'd like to be able to do this in general. This identification is important since often the rate of change is easier to measure or model than a given quantity itself. Let's suppose we have a car on a journey. We have that the velocity v of the car's motion is equal to the derivative of s with respect to time. Now, the velocity v is easier to measure. S, the displacement, is typically harder to measure on this journey. But we'd still like to be able to find s in terms of t by using an equation including the velocity v. It is also possible to use these methods to find the area under a curve. Let's say that we have the function y is equal to f of x. Then between any 2 points a and b, we might like to be able to find the area under the curve. We found areas before, like triangles or rectangles, but this is more general. There is a curve involved at the top. This reversing differentiation process is more commonly known as integration. Taking the equation dy by dx is equal to 2x and transforming it into the equation y is equal to x squared plus c is the process of integration. So what exactly are the rules for integration? We can consider differentiation and integration to be opposites. Given the same equation dy by dx is equal to 2x, we can form y is equal to x squared plus c. Going from the right hand side to the left hand side is differentiation. We differentiate the curve y equals x squared plus c to get dy by dx is equal to 2x. We've seen this before. On the other hand, going in the opposite direction is integration. Therefore, differentiation and integration are opposites. We are required to add a constant c to the integrated function, as when the function is differentiated, this constant will disappear. Let's take the derivative of x squared plus c. This is going to be equal to the 2x for the x squared and then plus 0 for the c. This is equal to 2x. Any constant value will have this property. It differentiates to 0, and therefore we have to have a general constant c because we couldn't know possibly what constant it was originally. The constant c added onto the original function is often called the constant of integration. Whenever we integrate some function and get, say, like we had before, y is equal to x squared plus c, this plus c is called the constant of integration, and whenever we're integrating, we always need to have a plus c. We can use notation for integration to describe the relationship between integration and differentiation more concisely. We write the integral of 2x, and then we write this dx is equal to x squared plus c. This is the integration symbol called the integral. The thing that we're integrating is often called the integrand. This strange dx symbol just means that we are integrating with respect to x. All this means is that we always have to have something here corresponding to the type of variable we have here. We couldn't hope to integrate something of the form the integral of 2y dx, unless we knew y in terms of x, and therefore secretly it is a function of x. And again, as before, we have this constant of integration. In general, we can form an equation describing the relationship between a function and its integral. Given a function little f of x, we can let capital F of x be the integral of little f of x. So we can have the f of x, and we're going to let this be the integral of our little f of x. This gives us the equation that when we integrate little f of x with respect to x, we get capital F of x plus c. This relationship is best summarised in a theorem called the fundamental theorem of calculus. If we indeed have that the integral of little f of x with respect to x is equal to capital F of x plus c, then it follows that when we differentiate capital F of x, we get little f of x. In general, this theorem summarises that these two are reverses. This theorem is called the fundamental theorem of calculus. This can be seen to mean that integration is the reverse of differentiation. Whenever we differentiate a function, we can also form a similar integration equation. Some important properties of integration follow directly from properties of differentiation. Suppose we have that y is a constant multiple of a given function little f of x. Then, from the rules of differentiation, it follows that when you differentiate y, we write y prime, that we get k multiplied by the derivative of f of x, f prime of x. And if y is the sum of two functions, say the function f of x and the function g of x, then when we differentiate to obtain y prime, this is the same as differentiating them in term and adding up the results. So we have f prime of x plus g prime of x. Now, these two results are results from differentiation, and we can apply them to get similar integration results. And so if we integrate a constant multiple of a given function of x, f of x, with respect to x, then we can bring the constant outside and have k multiplied by the integral of f of x with respect to x. And again, it's important to stress that k is a constant and not another general function of x. Similarly, if you integrate a sum of functions, say the functions f of x and g of x, with respect to x, then you can separate this out as two integrals. one of the function f of x with respect to x, and then we add this to the integral of g of x with respect to x. These two results can help us when integrating functions. Now, we often say that integration behaves linearly because it obeys the above properties, which are known as the properties of linearity. The properties of linearity may make you think of a linear function. Given the curve of y against x, a linear function is one which is a straight line. But in general, for an operator such as an integral, these are the properties of linearity, and therefore we say that integration is linear. So how exactly can we integrate ax to the power of n? We have previously come across the differentiation rule for power functions. Whenever we differentiate ax to the power of n, the result that we obtain is an multiplied by x to the power of n minus 1. We bring the power down and we reduce the power by 1. Reversing this formula gives the corresponding rule for integration. When we integrate ax to the power of n with respect to x, we have the a, and then we instead divide by n plus 1, and then we add 1 to the power to give us x to the power of n plus 1. And of course we have this plus c, the arbitrary constant of integration. Now, this result only holds for all n when n is not equal to minus 1. A different rule has to be applied in that case. Due to the linearity of integration, we are able to integrate any sums of these power functions. Let's suppose that we have p, q, all the way up to r, which are none of which equal to minus 1, and we're given some constants a, b, all the way up to c. Then if we write our function f of x as a general sum of these power functions, i.e. ax to the power of p plus bx to the power of q, all the way up to our final one, which is cx to the power of r. So if we want to integrate this function, i.e. to integrate f of x with respect to x, then all we need to do is to use linearity of integration and the above rule. And so what we get is a divided by p plus 1 multiplied by x to the power of p plus 1. Again, all we do is to add 1 to the power and divide by that power. Similarly, then we add, by using the properties of linearity for integration, b divided by q plus 1, and then we have a x to the power of q plus 1. And then we go all the way up, and our final term is c divided by r plus 1 multiplied by x to the power of r plus 1. And then we have to have an arbitrary constant. Well, we already use c, so we'll call it plus k. That is our constant of integration. Products of functions often first need to be converted into terms of the form ax to the power of n using the laws of indices before integrating. Let's say we have the product 3x plus 1 multiplied by x minus 1. Let's say that we want to integrate this. Well, it's a lot harder to integrate it in this form, but as soon as we expand this out and get 3x squared minus 2x minus 1, then the integration becomes a lot simpler because we have functions of the required form. These are all functions of the form a constant a multiplied by x to the power of n for different values of n. Even the minus 1 is really minus x to the power of 0. So then if we wish to integrate this function 3x plus 1 multiplied by x minus 1 with respect to x, then it is sensible to first expand out this and get 3x squared minus 2x minus 1 integrated with respect to x. We put a bracket around this function, i.e. the integrand, because it is necessary to see exactly what we're integrating. And then all we do is to apply the rule for each term in turn. So we have this 3x squared. We're going to take the 3, that's the constant outside. We're going to add 1 to the power and then divide by that, so we get divided by 3, and then we have this x to the power of 3, the power before increased by 1. And then we have a minus 2, that's the constant from the 2x, and then we divide by the new power, which is increased by 1 to the old power, where the old power is 1, and so we increase by 1 to get 2, and then we have an x squared, that's increased by 1 from before, and this minus 1 becomes minus 1, divided by the new power, which is increased by 1 from the old power, where the old power is 0, so the new power is 1, and then we have an x to the power of 1. Of course, we then have our arbitrary constant plus c, and then by simplifying all of these fractions, we get x cubed minus x squared minus x plus c. This is the result of our integration. The same is true for ratios of functions. Suppose that we want to integrate x squared plus 1 divided by x to the power of 3 over 2. In general, this would be quite hard to integrate in this form. What we do instead is to apply our index rules, and we get for our first term, by just taking the x to the power of 3 over 2 associated with our x squared, we get x to the power of 2 minus 3 over 2, that is our subtraction index rule, and then we add our x to the power of, well, 0 for the 1 minus 3 over 2. This of course becomes x to the power of 1/2 and then plus x to the power of minus 3 over 2. So when we integrate this function, x squared plus 1 divided by x to the power of 3 over 2, with respect to x, and now if we want to integrate this, it is much easier to have it in this form since we can apply our above rule. And so we use our index rules as we have done to get x to the power of 1/2 plus x to the power of minus 3 over 2. Then we put brackets around this and we are integrating with respect to x. Never forget the dx or the plus c at the end. So what we have here, we add 1 to the power and we divide by that power. And so we have a 1, which is the constant technically outside of this first expression, divided by the new power, which is 3 over 2, that's the added 1 to the 1/2, and then we have an x to the power of that power. So we have 3 over 2. And then we have a plus 1, again that's the outside constant next to this term here. And then we divide by the new power, which is minus 1/2, since we've added 1 to the minus 3 over 2. And then we have our x to the power of that power, minus 1/2. Then we do not forget the plus c. By flipping over these fractions, we get 2/3 x to the power of 3 over 2, minus 2x to the power of minus 1/2, and then plus c. Let's take a look at some examples. Our first example tells us that given that f prime of x is equal to x to the power of minus 3 over 4, find f of x. Our first step is to recall the fundamental theorem of calculus in the context of the question. The fundamental theorem of calculus, which I'll abbreviate as FTC, if it's the case that f prime of x can be written in the form d by dx of f of x for some function f of x, then this is the same as the integral of f prime of x is equal to f of x, and this gives us a method of obtaining our f of x. Of course, we also have this plus c for the constant of integration as well. Our second step is to recall the formula for integrating terms of the form ax to the power of n. When we integrate ax to the power of n for some value of n which is not equal to minus 1, then we get a divided by n plus 1, and then we multiply by x to the power of n plus 1, and of course we have the arbitrary constant plus c. Again, this only holds when n is not equal to minus 1. Our third step is to substitute the required values into the integration rule. By looking at our fundamental theorem of calculus and the question, we see that we've been given f prime of x is equal to x to the power of minus 3 over 4. And we can find the corresponding f of x by integrating this x to the power of minus 3 over 4. And as such, we're going to do that, so when we integrate x to the power of minus 3 over 4 with respect to x, and we use our rule we have above, Well, our a value is clearly 1, there's no constant outside, and then we divide by the new constant, which is the old power plus 1, and then we have our x to the power of our old power plus 1. And on the end, of course, we have the plus c. Our fourth step is to find the required integral, remembering to have a constant of integration. Well, we've already remembered that, so that's fine. By simplifying the above expression, we get that the integral of x to the power of minus 3 over 4 with respect to x is equal to 1 divided by 1/4, that is the minus 3/4 plus 1, and then we have an x to the power of 1/4, and then a plus c. So therefore we have found our f of x, because f of x is given by this integral, and it's equal to 4, that's the constant 1 over 1/4, x to the power of 1 over 4, plus some arbitrary constant unknown, c. And again, just in case, we have remembered to have that constant of integration. Our second example tells us that a curve has equation dy by dx is equal to 2x to the power of minus a half plus 6x minus 5. We're asked to find an equation for y in terms of x. Our first step is to use the fundamental theorem of calculus to write y as an integral. We currently have that dy by dx is equal to 2x to the power of minus a half, and then plus 6x minus 5. And so by applying the fundamental theorem of calculus, all we have to do to get y is to integrate this function. And so we integrate 2x to the power of minus a half plus 6x minus 5. And again, of course, we are going to have a bracket because this expression is so large, and we'll have a dx. This just means integrating with respect to x. Our second step is to recall the formula for integrating terms of the form ax to the power of n. Whenever we integrate ax to the power of n with respect to x, we get a divided by n plus 1 multiplied by x to the power of n plus 1. And of course we should not forget our plus c, the arbitrary constant of integration. Our third step is to substitute the required values into the integration rule for each of the terms of the sum. Let's apply the linearity of integration and split this up into 3 integrals. Our first integral is going to be the integral of 2x to the power of minus a half with respect to x. If we look at our power, that's our n value, and we have to add 1 to that and put it into the new power and divide by it. We take our minus a half and we add 1 to it, and we get 1/2. And so we divide by the 1/2, and we have an x to the power of 1/2. The constant on the numerator is the constant outside. We have this 2. And of course, we should not forget that we have a constant of integration. For now, I'll just write plus a constant. And then for our second integral, we have the integral of 6x with respect to x. Currently, the power on the x is 1, and so we're adding 1 to it, we're going to get 2. And so we're going to divide by 2, and we're going to have an x to the power of 2. The constant up here is going to be the 6, the constant outside beforehand. And of course, we still have this plus constant. Our last integral is the integral of minus 5 with respect to x. This is a constant term, and so when we integrate it, we're going to have a power of 1. So therefore we have this minus 5, we divide by the 1, and we have an x to the power of 1 plus a constant. Our fourth step is to combine the integrals for each of the terms in the sum to get the equation for y, remembering to have a constant of integration. We have that y is equal to the sum of the integrals, the integral of 2x to the power of minus a half with respect to x, plus the integral of 6x with respect to x, and then plus the minus 5 with respect to x integrated. And therefore, by substituting in our results, we have for our first result 2 over 1/2 x to the power of 1/2 plus a constant. Well, 2 over 1/2 is just going to be 4. So we have 4x to the power of 1/2. And then the constant we're going to leave to the end. For our next term, we have a plus 6 over 2x squared, which is 3x squared. And again, we're going to leave the constant to the end. And for our last term, we have this minus 5 over 1, which is a minus 5. And then we have an x to the power of 1, which is just x. Now we can bring in our constants. We add together our 3 arbitrary constants that we obtained above to give some general arbitrary constant, which we'll just call plus c. So all we've done is to bundle it all into one big constant, plus c. This is our solution for y. Our last example asks us to find the integral of 2x squared plus 1 divided by the cube root of x. Our first step is to write out the integrand as a sum of terms of the form ax to the power of n. The first thing to do is to write this 2x squared plus 1 on the numerator, but to make a slight change to the denominator, instead of writing the cube root of x, we can write x to the power of 1/3. This is equivalent. And then we can apply our index rules, and so what we get is we get a 2 outside, that's our constant, and then we have this x squared divided by the x to the power of 1/3. Well, that's going to be x to the power of 2 minus 1/3, which is 5/3. And then we have the plus 1 divided by the x to the power of 1/3. Well, it's just plus x to the power of minus 1/3 because we're dividing by it. Our second step is to recall the formula for integrating terms of the form ax to the power of n. When we integrate ax to the power of n with respect to x, we get the following formula. We get a divided by n plus 1 multiplied by x to the power of n plus 1, and again, we should not forget our arbitrary constant of integration plus c. Our third step is to substitute the required values into the integration rule for each of the terms of the sum. So our first term we need to integrate is this 2x to the power of 5 over 3. So we look at the integral of 2x to the power of 5 over 3 with respect to x, and we get the 2 outside divided by the power 5/3 added to 1, and so we get 8/3, and we have an x to the power of 8/3. And again, we have this plus arbitrary constant, which is called a constant for now, not plus c, we'll have that at the end. And then we have the integral of the second term, which is the integral of x to the power of minus 1/3. And so we integrate x to the power of 1/3 with respect to x. Our constant outside is just 1, and then we divide by the new power, which is minus 1/3 plus 1, and so we get 2/3, and then we have an x to the power of 2/3, and then we plus a constant. Now we're going to be adding up the two integrals, and so we're going to combine the integrals for each of the terms in the sum to find the required integral, remembering to have a constant of integration. So in general, we're looking for the integral of 2x squared plus 1 divided by the cube root of x with respect to x. And we've now managed to split this up into two integrals. Firstly, the integral of 2x to the power of 5 over 3 with respect to x, and secondly, the integral of x to the power of minus 1/3 with respect to x. We've seen that we've calculated these integrals, and so we have 2 over 8 over 3 for the first constant, and that is 3 over 4, since we get 6 over 8 and then cancel. And so we have our 3 over 4 as our constant, and then we have an x to the power of 8 over 3. That's our first term. And then for our second term, we have a 1 over 2 over 3, which is 3 over 2 for our constant, and then we have an x to the power of 2/3. And now we bundle the constant into 1 and have a plus c. This is the sum of the two constants we have here.
Hey guys, I hope you enjoyed the video. If you are looking for an amazing A-level maths resource, join me today in my series of engaging bite-sized video tutorials. Just click the SnapRevise smiley face, and together, let's make A-level maths a walk in the park.